Welcome back, Professor Bright here, and we are going to begin our Chapter 7 discussion. And in this section, we're going to talk about diagonalization. And to do that, we're going to first introduce what we call a discrete dynamical system. The two ideas are linked, but not necessarily all the times, but they happen to coincide nicely in our discussion here. But before we get into that, I just want you to do this warm-up, pause the video, try it out, and resume the video when you're ready to see the answers. And here you go. Okay, warm-up aside, let's move on to the dynamical system idea. So what we're going to begin with is looking at two populations that are interlinked and how those populations change over time. So we're going to look at coyotes and roadrunners. And if you've ever seen Looney Tunes, you know there's Wile E. Coyote and the Roadrunner. Doesn't have a name. But so that's the idea that we're going to kind of play off of here. Okay, but the idea is that we call this a dynamical system because the change in one population is linked to the change in the other one. So the number of coyotes and roadrunners that are present is determined by how many there are the previous year. Okay, and in particular, we can say maybe this is the model that we're going to go with. So the number of coyotes for the next year is based on both the coyotes and roadrunners from the previous year, and similar with the roadrunners. Okay, C is coyotes, R is roadrunners. Okay, and we're going to say, just in general, we're going to let the vector x of t represent coyotes and roadrunners in the first and second positions respectively. And when we use this notation, we call that the state vector. So again, just saying how many of each there are at a certain time. Okay. So then the next question that I want to represent before we go on too far is, what is the domain and codomain of x of t? Okay. So pause video, see if you can fill out that piece of information. Okay, well, if you think carefully, it takes a value of r, in r, so that's t, and it produces a two-dimensional output. So this is something interesting that we haven't seen before. Normally we narrow the dimension as we go on. This one, we expand the dimension. Huh, that's interesting. But now, again, we want to know about this population, what happens over time. So we are curious what x of t plus 1 is. Well, according to the definition, it is just going to be c of t plus 1 over r of, and then the second position would be r of t plus 1, which we can expand and write that as 0.86 c of t plus 0.08 r of t. Okay, just using the equations from above, right? And then similarly for the next one, negative 0.12 c of t plus 1.14 r of t. Okay? And that's all we need to do. If we wanted, we could write this a little bit differently and just write this more in matrix notation. So it'd be 0.86, negative 0.12, 0.08, 1.14, and then c of t, r of t. Okay, so that's fine. Now what we want to do is we've determined an algorithm. Now let's actually do the calculation. Okay, so x of 0, we're saying we begin with 1,000 of each in the population. And now what happens, what is x1, x2, x3? Okay, now I trust you can do this calculation. I'm just going to write this first one out and then give you the answers. So 0.86, negative 0.12, and then 0.08, 1.14, and then times 1,000, 1,000. Okay, this, after you do the calculation, gives you, I got 940 for the coyotes and 1020 for the roadrunners. X2, if you do that same process, so you would use, you would do the same matrix and then times 940 and then 1020, because that's our new population, right? So then when you do this, I got 890 and then 1050. Okay, and so now I haven't done x3. We could do that, but I do want to take a moment to look at an image of what it would produce. So in this graph you can see the horizontal axis is C for coyotes and R is the vertical axis for roadrunners. And so if we kind of go down one, great, we get that one. Okay, so notice how the points move. Again, we don't have a scale here, but you get the idea. Okay, and then for x of 2, we get that. X of 3, we get that. And if we were to continue, we would get a path that looks something like this. So this is as t increases, it would go this direction. Okay, now let's say we ended up looking at a different, oh, that doesn't erase that well. There we go. We had a different starting value. Okay, and so now population has a different starting value. Again, as we look over time, there's the progression, and eventually we would continue, and it would produce this hyperbolic shape. That's kind of interesting. Now, we're going to study why this happens and how we determine the shape, more generally speaking. So you can look forward to that in future videos.